The main new thing here is the generate key pair, create a key pair. And it turns out to be pretty simple because we just use generate key with the correct parameters for generating an RSA SSA key. We want the key to be exportable, and we're going to use this key for digital signing and digital verification, so sign and verify are the usages. Then given a key pair, we need to export both of those keys. Well, exporting the key is an asynchronous operation that returns a promise, so we can write them one after another, but when they execute, they're going to be executing at the same time. So the first one we write is to export the public key. Let me make this a little smaller so it fits better. So we're going to say export the public key, and that's going to give us a buffer in SPKI format. We're going to base64 encode it and put it in the proper place in the dialog box or show an error. Then we're going to kick off exporting the private key into PKCS8 format and do the same thing with the result, convert it to base64 and put it in the box. Now, we're going to have the first export key returned before the operation finishes, so the second export key is going to start and they're both going to be going on at the same time. In fact, either one of them may be done first. In this case, we don't care. The user is not going to actually ask to sign or verify anything until both keys are visible in the web page. But if we did have an application where it mattered that we needed to have both those separate asynchronous operations finished before we started another one, we'd have two options. We could chain them, so we'd do one of them and wait for it to be finished and then start the next one. Or we could be more efficient by doing them both in parallel. And the way you can synchronize multiple promises is using something called promise.all. I'm not going to do an example of it because we don't need it, but you might want to look it up. It is a way that you can have an array of promises, each of which is their own parallel asynchronous operation. And that will return a promise that will resolve once all of them have resolved. So you can do them all and get them synchronized again. But that's all that's involved in generating the key pair. Signing a file is almost identical to the symmetric encryption we did for password-based key derivation. We use a different method, but the steps are very, very similar. We get the key out of the form element. In this case, it's the form element for the private key because that's what we use for signing, and import it to become our private key. The imported key does not have to ever be exported. We already had an exported version. And this imported key is only going to be used for this one operation and then discarded, so we only need to have for its usage the one thing we're going to do, which is signing. So once we have a private key, we set up the file reader, and the success handler for the file reader is going to take the document, and it's going to pass the document and the private key to the subtle crypto sign method. Very straightforward. That's going to return a signature in a buffer. We base64 encode it and display it in the form. That's all there is to it mechanically. The tricky thing is keeping track of the fact you've got to do it. Verifying a signature is somewhat similar, except the input to the verify method has not only a key and a file, it also has the signature. It doesn't produce a signature, it needs to be given a signature. So we're going to pull the public key out of a form element. We're going to pull the signature out of a form element. Then we're going to import the key to get a public key, crypto key object. We're going to read the file, and when the file is finished being read, when the file is finished being read, we're going to call the verify method, which returns a promise that on completion yields a Boolean. True if the verification is valid, false otherwise. So if the Boolean is true, we're going to pop up an alert saying it's a good signature. Otherwise, we're going to pop up an alert saying it's a bad signature. If it just is gibberish and it couldn't verify it one way or another, we're going to pop up an error message as to what the problem was. So those are the steps. And as I said, unlike a lot of the other stuff we've done, this has a lot of real practical usages. You can have your user community each use a program that generates the key pair, tell them, save the private key on your machine, don't share it with anybody, but here, fill out a web form where you give us the private key and your name and address. We'll check that you're not lying to us and we'll keep it in a database. And from that point on, you can digitally sign things and we can verify if they're really yours or not.
How much of the asymmetric stuff is cross-browser?
All of the stuff we're seeing now works on every browser I've been able to try. I haven't tried it with Internet Explorer 11 because I'd have to modify it, but I believe it works there as is. And it definitely works on Firefox and Edge and Opera and Chrome. In fact, not only that, it works on the Chrome browser on this wristwatch. All the ones we've seen so far work on the wristwatch. Now, I cannot give you a practical use case for that. The Chrome browser actually pops up a little on-screen keyboard. Shows you about 3 letters at a time. You got to scroll around to be able to use any more of it. But the fact that you can do it at all is something I care about. Okay, this is the last lab we're going to really do hands-on. We're going to talk about Lab 5, and I'm going to explain why we're not going to do hands-on with it. We're just going to go over how it is so you can study it for yourself. But this one we're actually going to develop our own solution for. Lab 4, where we're going to use public key cryptography for secrets. This is practical. You can go ahead and create a key pair, save your private key, and on your website put your public key. Then anybody in the world seeing that public key can encrypt a message and send it to you, and you're the only person that can ever decrypt it. This is something journalists find useful if they're really concerned about somebody snooping on them on what their sources are sending them. Because anybody in the world can send them something, not just somebody the journalist has previously met, and only the journalist can then decrypt it. However, this should be simple because all we would do is use the subtle crypto encrypt method, but give it our public key. But that won't work because there are limitations in public key cryptography, partly that it's slow, so it'd take forever to do a lot of data. But the bigger one is, for instance, the RSA algorithm cannot encrypt very much data. It's limited by the size of the key. So you can't encrypt anything larger than perhaps 1,000 or 2,000 bits long, not all your general ciphertext. This didn't come up as an issue for signing because the signing operation did its encryption under the hood, and it only used public key encryption to encrypt or decrypt the message digest, which is small, only 256 bytes. But here, if we want to send somebody a really secret message that might be really long, we would run into that limitation. So the solution, and the reason this lab is tricky, is we have to use a symmetric asymmetric hybrid. What we do when we want to send somebody a secret message using public key cryptography is we first create a symmetric key at random, one that only we know. We haven't shared it with anybody yet. We encrypt that symmetric key with the public key. We can use public key cryptography on the symmetric key because it's not a very large piece of data. We also use the symmetric key to encrypt the original message. So now we've got 2 pieces that we have to give the person we're trying to talk to. We give him the ciphertext. He's going to need to know the symmetric key to ever decrypt that ciphertext. But we also give him or her the encrypted session key. It's encrypted with public key cryptography. We encrypted it with the recipient's public key, so the recipient's the only person that has the matching private key. So when the recipient gets the message, they use their private key to decrypt the session key. They then use the session key to decrypt the message. Now, going through it, it's actually logically not too complicated, but it is surprising doing these 2 cryptographic operations together. I often just kind of tripped over my own feet. You got to be careful trying to make this work. So our goals for Lab 4 are going to be, first of all, to create a key pair useful for encrypting and decrypting and put it in form elements. This is going to be almost identical to what we did for Lab 3. But then, when a user selects a file and clicks a button, we're going to want to not sign the file, we're going to want to encrypt the file. So we're going to encrypt it by creating a random session key, encrypting that session key with the public key, and then encrypting the file with the session key. Now normally we would package the encrypted session key and the file together into one file. But we're not going to do that because we did that with the IV and it wasn't too hard because somebody could get it and know that the first 16 bytes are the IV. The encrypted session key could be a variety of different lengths, so our packaging would be more complicated. It's certainly doable, but we don't want to take time on it. So we're going to put the encrypted session key visible in a form element and download the ciphertext file. Later, we're going to want to decrypt. We're going to select a file and have filled in the encrypted session key. And what we're going to do is we're going to use the private key to decrypt the session key, and then the decrypted session key to decrypt the ciphertext. Let's take a look. We'll generate a key pair. We'll select a file. And when we say encrypt, it's going to create a random session key, encrypt it with the private key, and put the session key there, and download the encrypted plain text, the encrypted ciphertext. So to decrypt, we select the encrypted ciphertext, use the encrypted session key, and say decrypt, and we're going to get the original file back. In order to actually look at it, we're going to have to change its file suffix to JPEG so it knows what to do with it, and we get the original file back. And this is actually practical. This is how you can share keys. The cool thing about public key cryptography is it's only been about 40 years since anybody even thought it would be possible. Symmetric cryptography is thousands of years old. Julius Caesar used symmetric cryptography. We wouldn't have much trouble breaking it today. In fact, if you were a kid on highway rest stops, you probably got little placemats with encrypted messages that were more sophisticated than what Julius Caesar used, but it was still symmetric cryptography. Public key cryptography was invented 40 years ago approximately by Whitfield Duffy and Martin Hellman. And just last week, they were awarded the Turing Award for that achievement, which is the biggest award in computing. It is an enormous achievement. It has enabled all of the secret communication we do, all the e-commerce we do over computer networks. Couldn't happen without it. Now, it turns out that public key cryptography was independently invented about 5 years earlier in England, but it was kept secret. It was invented by the government, kept secret, and nobody knew about it for decades. So it didn't make any impact on the world like what Duffy and Hellman did.
How would you get around the
Diffie Hellman, rather, not Duffy.
how would you get around the, is that just something that limitation or something just not the file extension?
I'm sorry?
The file extension having an appended.
No, the file extension is just because when I go to open a file in Windows, it doesn't know what program to display it with, unless I have a file extension. But for instance, if I use a Unix-based operating system, it actually looks at the file and says, oh, that looks like an image, and will just show it to me properly.
Correct, but what I'm asking now is, what would be the implementation for if you were to use a website to say, oh, this file is a JPEG, this one's a text file, and append it for the user so they want to do it themselves?
For real-world encryption, the user is going to get the plain text back, but needs to know, is that plain text a text file, a Word file, a JPEG image? So in the real world, you're actually going to, the original plain text you encrypt is probably going to be a data structure that has the contents of the file and also has the MIME type and maybe the file name and everything. So when the person decrypts it, they can know that, hey, what he sent me was a file that should be called, myphoto.jpg, and it's a JPEG image.
So we're just make sure I understand. You're going to take the original string and append the type, maybe the name, other piece on the end of it, and then when you decrypt it, you look at that last.
Right. So in real life, what's encrypted as a plain text wouldn't just be the file. It would be the file plus some metadata that would tell you how to use the file when you decrypt it later. And that would just about double how long it takes to build this exercise. So, all right, so in order to do this encryption, you're going to need to use the RSA OAEP public key algorithm. It takes the same parameters as RSA SSA PKCS1. The symmetric encryption part, we're just going to use our old standby AES CBC with 256-bit keys. So let's take almost 15 minutes for this one. And then we'll come back and use the last 15 minutes to talk about the last lab and do a little bit of cleanup. Okay, let's start taking a look at the solution of this. There have been a lot of questions about the practicality of this example, and in fact, it's not a fully practical example, because if you encrypt a file with a secret for somebody, you've got to give him two pieces. You've got to give him that encrypted session key that we're showing in the form, and you've got to give him the ciphertext we download. As a practical matter, what you'd want to give him is one file that has all those pieces in some format that he understands so he can take the pieces apart. There are standard formats that do all that. They're more complicated than we really could get into right now, but the next lab, Lab 5, is going to talk about some of them. All right, let's take a look at the solution here. Lots of it is very, very similar to the solution for Lab 4, for Lab 3. We're We're creating a key pair, and it's basically exactly the same thing we did to create a key pair in Lab 3, except that we're using the RSA OAEP algorithm, and our usages are encrypt and decrypt. By the way, notice that parameter that's 65,537 says new uint 8 array 101. That's because the integers that need to be given to this web crypto library are long integers. They may be 1 byte long, 2 bytes long, 700 bytes long. The number 65,537 takes 3 bytes. So we are generating a sequence of 3 bytes whose binary representation is 65,537. So we're going to generate the key, then we've got the key pair, and we're going to do an export key for the public key into SPKI format, and an export key for the private key into PKCS8 format. Put them in the dialog box for the users to use later. Now, when the encrypt button is clicked, the user has to have already filled in the public key because we're going to encrypt it to the public key. So the first thing we're going to do is take the public key out of the form and import it to get a crypto key object. Now is where we start deviating from what Lab 3 looked like. In Lab 3, once we had the public key, we could read the file and we could sign it. But in fact, we can't read the file and encrypt it yet because we cannot encrypt the file with the public key. The file is too long. So the first thing we're going to do is generate a key, a session key. And once we get the session key, we're going to need to do 2 things. We need to use that session key to encrypt the file to get our ciphertext. And we also need to export the session key and encrypt the exported session key so that we can provide that to the user. Since we're not packaging this together in one file, we can do these 2 operations in parallel. So part 1, we have a key. We can encrypt the plain text to get ciphertext using AES-CBC encryption. So we're just going to go ahead and do that. We're going to set up the file reader. When the reader is completed, we're going to run encrypt the file we read. To encrypt the file we read, we're going to create an initialization vector. We're going to take the plain text that the reader had, use the encrypt mechanism with AES-CBC, and for the blob, we're going to build a new blob consisting of the IV followed by the ciphertext, and have the user download it by forcing window location to be that URL. That's what we did in Lab 2. Part 2, nobody's going to be able to decrypt that ciphertext we created unless they know the session key. And we can't just give them the session key because somebody can intercept that. So part 2 is solving that problem. We're taking the session key and we're going to export it. Well, we've already exported it, so we're going to export it. That gives us a buffer with bytes, and we want to encrypt that buffer using public key encryption. So the session key buffer is the session key. We're encrypting it using our public key. That gives us an encrypted session key, which we're going to put in the dialog box. We've got to provide both those things, the ciphertext file that was encrypted with the session key and the encrypted session key to the user who receives this. And that's what the decrypt function will do. The decrypt function starts out by importing the private key that's needed for this decryption. Once it's got a private key, the first thing it needs to do is get the session key that was used for the ciphertext. What is being given is the encrypted session key. So it takes the encrypted session key out of the form, gets it in a byte array, and uses RSA decryption to decrypt that session key and get the original session key bytes back. Now we need to have a key to do the decryption, so we import that to get the session key itself, and then we decrypt that AES-CBC ciphertext, doing a file reader exactly the way we did in Lab 2. No piece of this is terribly hard. Getting the pieces to work, even if you're familiar with it, likely is going to take a little while. So you may want to go and take this with you and study it. And the reason is you're doing 2 different encryption operations and 2 different decryption operations, and it's terribly easy to get confused as to when you're dealing with one or the other. The other thing that's confusing is each of those has multiple asynchronous steps, and it can be confusing as to what has to be done in what order. But that is the most practical web application we've created. Again, you can create a key pair you can publish your public key at your website, and anybody in the world can send you messages now that only you can decrypt. All right, Lab 5. We're going to go over this very, very quickly because I really wanted to leave you with an example to refer to in the future. Because Lab 5, we're going to do a self-signed X509 certificate. And what a certificate is a data structure that contains a public key and identifying information of the holder of the public key and its matching private key. Here we're getting into the standard data structures for keys, exchanging messages, and so forth. What makes this thing a certificate is a third party has digitally signed it, a party that you already know about. For example, it might be VeriSign or Thauti has signed the certificate and said that I've checked the identity that this certificate says it's for, and it really is this person. So if you trust the certificate authority, you can then trust the public key in the certificate. X509 is the standard format for certificates, and it's the reason we're not going to do a hands-on lab because it's horrible. It's just plain horrible. It comes from a set of standards, the X500 standards that were created 30 years ago by the International Telecommunications Union and the Open Systems Interconnect Initiative. And any of you who were, the very few of you who might have been around back then and involved in computing, know that the way we approached things then was extremely technical, complicated. We wanted everything to be extremely compact. We wanted everything to be error-free as opposed to possibly detecting errors. We wanted everything to be unambiguous. And the X509, the X500 family, in fact, are all those things. It created something called ASN.1 for abstract syntax notation. It's kind of like an abstract language-independent data structure. And that can be serialized into a binary string using what's known as basic encoding rules or distinguished encoding rules. And that is what the SPKI exported public key and PKCS8 exported private key are in the DER encoded ASN1. And that format is the reason that when you look at the exported file, you see the beginning to be the same, because the header information of those data structures is the same in each case until you get further down. Very compact, which was important. Networks were unbelievably expensive back then, as was storage. Unambiguous, and as I say, horribly complex. That complexity is the reason we're going to see the lab, but we're not going to try and build it ourselves. So here we have a certificate that has identifying information about somebody. And now we can say create a certificate. The certificate data structure has been base 64 encoded, so it is the distinguished encoding rules export of that ASN1 data structure converted to base 64. It's the sort of thing you see if you've ever run your own web server with SSL. The public key, we exported that. It's already part of the certificate. And then the private key in PKCS format. Now, how did that work? Well, you've got two options. In order to do the stuff we just did, you don't do any new cryptography. The only cryptography that we did in there was create a key pair. We've seen that before. That's still going to be done with web crypto. But once we get that, we need to create the appropriate data structures. We're going to create a certificate data structure. The details are really tough, so we're not going to do it from scratch. A couple of years ago, I did figure this all out to my own satisfaction, and I blogged about it. You can go look at those blog posts if you want to see how you actually, by hand, can construct ASN.1 DER encoded objects and deconstruct them. But shortly after I did that, I discovered that other than learning how horrible it was, I really didn't need to have done that, because there's a library out there called PKI.js that is really, really good. It's built on top of web crypto. It doesn't do any crypto itself, but it handles all these data structures. It does a lot more than certificate creation. It does digital signing using the same family of standards that X509 certificates have. It does encryption, etc., all those things. It was written by somebody who clearly is more of a traditional C++ or Java or C# programmer, because all of the methods and data objects are named org.pkijs.simple.something. Org.pkijs.simple.cert constructs an X509 object. So you create an empty object, you set its properties, and then you use a method as part of the library that converts that to ASN1 and another method that converts the abstract data structure to the DER serialization. There are a lot of these different data types like org.pkijs.asn1.integer and so on. And you can take a look at the solution. Well, before we do take a look at the solution because we've already seen the application. And creating a certificate gets the identifying information strings out of the field, creates a key pair, and then once we have a key pair, it can build that certificate. If we go down to build certificate object to see how that works, it creates a cert object. It sets properties, the serial number, which it sets to the Linux date, so it'd be unique. The subject, which is who the certificate is given to, the person that the certificate identifies. The issuer, which is whoever's signing and standing behind the certificate. This is going to be a self-signed certificate, so we stand behind ourselves. How long is good for? Set up an array of extensions so that we can put in 2 extensions that are important for certificates, whether it's a certificate authority certificate and what the keys can be used for, and then what the algorithms are. And while we thought RSA SSA-PKCS1-V1_5 was a bad name, in the world of X509, the name for that algorithm is 1.2.840.113.549.1.1.11. Unambiguous. We set the public key and sign it. So you can go over and take a look at this, and you're either going to say, I'm so glad I don't have to ever do this, or you're going to say, I'm so glad that this at least helps with this horrible thing that I have to do. In my company, we have to do it, and this has been a huge help. This library is still regularly maintained. The maintainer is fully accessible. You can submit bug reports or email him, and he'll be very responsive. So, to sum up, we've spent a half a day talking about the Web Cryptography API, which is important because it enables end-to-end secrecy on authentication. It allows our end-user application to talk to another end-user application and not let anybody else involved in passing the data back and forth interfere with our communication. It uses well-established native libraries for performance and security, and it's stable, pretty stable. There are some algorithms in the API that may be removed when we move from candidate to proposed recommendation because nobody supports them. But the algorithms we've looked at and quite a few others are well supported by multiple browsers, and they will be staying in the API. The interoperability is also good. All this stuff we did, the reason we put stuff in those dialog boxes in text encoding is you could copy that data to a different browser on a different machine and a different operating system and still use it. If you want to learn more about cryptography, the concepts behind it, we really focus more on the mechanics. I recommend that you take the time to take a free online course from Coursera called Cryptography 1. It lasts 6 weeks. If you want to get a certification that you pass it, you have to pay money, but if you want to just take the course, it's free. The next offering starts next Monday. I took this a little over 3 years ago, 3.5 years ago, I guess, and I had been using cryptography, as I said, since the 90s. I still learned a lot. I found it really valuable, really worthwhile. It's taught by a Stanford professor named Dan Bonnet, who is a world-class cryptographer and very good at explaining the concepts. After you've taken that, you're going to want to take Cryptography 2 from him. And that's going to be offered right after Lucy finally lets Charlie Brown really kick the football. I took this in 2012. They said we're going to offer Crypto 2 in a few months. They issued it in the catalog. We got closer to when it was supposed to be. They moved it back. Got closer to when it was supposed to be, moved it back. They've been doing that now for over 3 years. The most recent time, 2 days before it was supposed to start, they moved it back 5 months. But someday it might be offered. I'm really looking forward to it. The resources I've mentioned before, the Web Cryptography Candidate Recommendation. There's also a browser crypto test page that a GitHub user has put out. If you go to that test page, it will try all the algorithms defined in the API and build a table telling you which ones work in that browser and which ones don't. It's really useful. Also, as somebody noticed, I gave a talk at Fluent last year on the Web Cryptography API. It was a much shorter talk, and it was more on concepts than the hands-on stuff we've seen today. But I created a page full of resources at engelkey.com/fluent. Those resources are still valid, and it also has the slides from last year's talk and a video of last year's talk available there. If you have any questions, feel free to buttonhole me here at the conference, or you can email me. My email address was fluent@engelkey.com. You'll have to look at the slides or the conferencing to know how to spell Engelkey, but that's really the only hard part in being able to reach me. And I will be putting up the video of this talk when it's available at my webpage at engelkey.com. So, I thank you guys for your patience. This is really complicated, deep stuff, and you've all stuck it out. I can't tell you how much I appreciate it. I hope it has been useful for you as well. Thanks.